Homework 18, section 8.3, confidence intervals for population proportions, video 2. Forgot to change this. All right, before we get into the steps for constructing a confidence interval for P, there are some conditions that have to be met in order for this procedure to be valid. If any of them aren't met, then it would require techniques that are beyond the scope of this course. So anytime you're asked to construct a confidence interval, these conditions will be met. You may be asked to verify that some of them are met. 4 conditions. Number 1, this one's fairly standard, simple random sample. I will admit that my sample was simple, meaning that everybody has a chance to take it, because when I posted the survey on Facebook, I made it public. Of course, some people will have an easier time finding it, mainly my own Facebook friends. Well, that would make it a random sample. Everybody has a chance of taking the survey. Is it a simple random sample? I'll be honest, not really, because not everybody on Facebook has the same chance of taking the sample. Namely, people who are my friends on Facebook have a better chance of taking the survey than people who aren't, unless people just go searching and happen to stumble across it. But let's put that to the side for a moment. Should be a simple random sample, or as simple and as random as you can make it. Number 2, the population size needs to be greater than 20 times the sample size. So in other words, your sample cannot be more than 5% of the population. Because if it were 5% of the population, 20 times 5% is 100%. So that's another way of saying this, is that your sample must be less than 5% of the population. I actually like that version of it better. It's just the way the author states it. The population is at least 20 times as large as the sample. The problem with this is you usually don't know how large your population is, but it's usually so large in comparison to the sample that it's an irrelevant point. So just make sure that your sample is not bigger than 5% of your population. Number 3, there are only 2 categories. This one's actually easy to get around. The 2 categories here are the people said yes or the people said no. But if you had a question with multiple answer choices, like what state were you born in? Texas, Louisiana, Oklahoma, Vermont, whatever. That's clearly more than 2 categories, but you can make it 2 categories by saying you were born in Texas or you weren't born in Texas. And then the 4th criteria is that the sample must contain at least 10 individuals in each category. So the sample must have at least 10 individuals in each category. So in the context of my survey question, I needed at least 10 people to have said yes and at least 10 people to have said no. Well, there were 60 and 35 of them said yes, so the other 25 said no, so we're okay there. So simple random sample, population is bigger than 20 times your sample, which is equivalent to saying that the sample is not more than 5% of your population. Only 2 categories, but if there's more than 2, then you make it 2 by saying you're either this category or you're not. And the sample has to have at least 10 individuals in each category. Now, if those criteria are all met, and in your homework they will be, then you can build a confidence interval the same way that we built one for a population mean. We just have to make a few adjustments. Now, I'm going to be going back and forth between the steps and actually doing an example. Let me check the time on this video. I may do the example in the next video. Oh, we're good. We're only at 4.5 minutes. All right. So, how do you build a confidence interval for a population proportion? The first step is the same as it was before. Obtain a point estimate. That's actually the general first step for any confidence interval. In this case, since we're estimating P, we need a value for P hat. Now in this problem we already have one, it's right here. We calculated it in the previous video. In several of your homework problems you will have to actually calculate the P hat value, but it's just turning a fraction into a decimal. The second step is to use the confidence level to find the critical values In other words, you have to know how to use the 95% to come up with a value for Z. Recall how the confidence level is used. The confidence level represents the center area of a standard normal distribution, meaning a Z-curve, if you will. So we need to cut off equal sized tails and put 95% of the area in the middle. Remember that the total area is 100%, and so the remaining two tails, compensate for the remaining 5%. 100 minus 95 is 5. So if these two tails collect together are 5%, then each one of them is half of 5%, or 2.5%. So this Z, we could call Z subscripted with 0.025. Remember, when you have a Z subscripted with a number, that number represents the area to the right of it. We could call this Z subscripted with 0.975 for the 97.5% to the right of it, but because of the symmetry of the picture, this is just going to be the negative of this Z value. So which one are we going to look up in the Z chart? Well, your Z chart tells you left areas, and so let's just look up this one. So this left area is 0.025, but in your Z chart the areas have 4 decimals, so let's put a 0 there. Go to your Z chart, either the one you have pulled up in Canvas, or maybe you've printed one out, or you pulled up the one in the homework. But if you go inside the Z chart where all the areas are, and go to the negative 1.96 row, you will find exactly 0.0250. So just a real quick picture. In the negative 1.96, in the negative 1.9 row, under the 0.06 column, you will find precisely 0.0250, which means the left Z-score is negative 1.96. So the negative Z is negative 1.96, which means the positive Z is positive 1.96. You only need one of them. Doesn't matter which one you get. All right, so that's the same as it was in the confidence interval for a population mean. Stick the confidence level in the middle, cut the remaining percent in half for each tail, use the Z table to find either Z value, and remember that they're opposites. Your third step is to calculate a standard error, which I abbreviate SE, although the author does not use the phrase SE. Now, you may have noticed that the standard error that we had in the previous series of videos was the same as sigma sub x bar, and I think I actually stated that. But we can't do this. We can't say sigma sub p hat. Why can't we say that? Because the formula for sigma sub p hat was this when we were doing probability problems involving proportions. But why can't we calculate this? Well, the answer is it contains a value that we don't know. We don't know population proportion. We're trying to estimate it. If we knew it, we wouldn't have to estimate it. This actually occurs more often in statistics than you would think. If you take more statistics class, you'll see it happen. That you need to calculate something based on a population value that you don't have. The standard protocol when that occurs is, instead of using the population value, use its point estimate, use its sample equivalent. So instead of using P, we're going to use P hat, because we have one of those. And instead of calling this sigma sub P hat, it would actually be called S sub P hat, since we're using a sample proportion instead of a population proportion. Now, I don't believe that this author at any point ever calls the standard error S sub P hat. So I am going to remove that and just say that you need to calculate your standard error. And it's the same formula we saw previously, except the p's have hats on them. All right, so let's calculate the standard error. It's the square root of a fraction whose denominator is the sample size, so you need that. And the numerator is the p hat 0.583 times 1 minus that p hat. And by the way, the 1 minus p hat value, that's the percent of the population that doesn't, the percent of the sample that doesn't have a characteristic. So 58.3% of them said yes. If I subtract this from 1, the remaining 41.7% of them would have said no. All right, so let's calculate that. Really need a better calculator than this one. It's got a square root, so it'll do for now. Okay, so 0.583 times, this calculator doesn't have parentheses, it's 0.417 times 0.417 divided by 60 equals, now a very common mistake here is to forget to do the square root at the end, so make sure you do that. Square root, and we'll take it to 4 decimal places, 0.0637. This number will always be small because the numerators are always decimals less than 1. So it's not uncommon to take this out to 4 decimal places. So there's our standard error. The hard part is over because the fourth step is to calculate the margin of error. And in any confidence interval, if you take statistics 2 at UT Tyler, you'll probably take me and you'll hear me say this again. On any confidence interval, the margin of error is always the z-value times the standard error. So we simply have to calculate 1.96, that was our z, times 0.0637. And again, that will come out to a lot of decimal places. My rule of thumb on any calculation, if it goes beyond 4 decimals, round it to 4 decimals. We get 0.1249. So there's our margin of error. And then the last step, as it was with the confidence interval for population mean, is to calculate the interval. Now, the whole premise behind a confidence interval is you start with the point estimate and then add and subtract a margin of error to it to open up an interval. Our point estimate here is p hat. And to that, we're going to both add and subtract the margin of error. So let's do that over here. Our p hat was 0.583. And to that, we are going to both add and subtract our margin of error, which was 0.1249. And so there's a variety of ways that we can answer this, but we're going to answer this one in the phrase from one number to another. The first number is the difference, so 0.583 minus 0.1249 is 4581 to the sum, so 0.583 plus 0.1249, 0.7079. I do want to remind you that there are multiple ways to represent a confidence interval. I'll have to erase this. You can say the phrase from the lower number to the upper number. You can write a compound inequality by saying the lower number, 0.4851. I did again, 0.4581. You can say the lower bound is less than the value that you're estimating. We're estimating P, population proportion, which at the same time is less than the upper bound, 0.7079. You can also write it using what's called interval notation. Basically, you just put the numbers next to each other, comma in between, whole thing in parentheses. But I want to also remind you what this means. This means that, or how to interpret this, we state with 95% confidence that the percent of all Facebook, we'll abbreviate it FB, users with the same opinion, about whether or not life will be back to normal in 1 year, is between, and since we're describing a percent, let's turn these to percents, 45.81% and 70.79%. So that would be in the interpretation. Honestly, it's not that difficult to calculate as long as you remember how to use the confidence level and the Z-chart, and you can follow the formulas, and that you can interpret the results. We'll take a look at another example in the next video. Ooh, that was a long video. I should have paused. Yeah, well.